Thank you. So our setting will be the normalized quadratic family parameterized by the Mandelbrot set, in particular one of its less well understood parts. So the Mandelbrot set has this central hyperbolic component bounded by a cardioid, and attached to it are these smaller satellite copies of the Mandelbrot set, which are indexed by rational numbers. Now, these satellite copies, in turn, have their own central hyperbolic components and attach to them second-order satellite copies, and so on and so forth. We say that PC is infinitely satellite renormalizable in the normalization theory of Dodi and Hubbard, if and only if it lies in an infinite intersection of these nested satellite copies. And then the sequence of rational numbers indexing each successive copy is called its combinatorial type, tau. We will be interested in high combinatorial types. That is, we can write out each of the indexing rational numbers as a modified continued fraction, modified because these epsilon ij can be plus or minus 1 as opposed to just 1 in the standard continued fraction. We say that tau is of high type greater or equal to n if all of these coefficients bij are greater or equal to n. So in practice, this means that each successive satellite copy is close to the root point of its parent copy, or the cusp of the main hyperbolic component. And the indexing rational numbers are of high type. Chiragi and Shishikura have connected satellite renormalization to another renormalization theory, the near parabolic renormalization of Ino and Shishikura. They have proven that there exists an n such that for all tau of high type greater or equal to n, there exists a C tau in the Mandelbrot set such that PC tau is infinitely satellite renormalizable of type tau, and also PC tau is infinitely near parabolic renormalizable. I will explain this later. We'll be interested in the post-critical set, that is the closure of the orbit, the forwards orbit of the unique critical value. Chiragi and Pedramfar have shown that this post-critical set is topologically either a Cantor set or a hairy Cantor set. So a hairy Cantor set is a topological object which enjoys many of the same universal properties as the Cantor set. However, its components are either single points or Jordan arcs, also known as the hairs. So I will just roughly show you how the Cantor set and the hairy Cantor set can emerge as intersections of nests of disconnected subsets of the plane. So here, we see that each nest converges to a single point, but here, while some nests converge to a single point, others have their diameter bounded away from 0. But so this is speaking very informally. They can also get contracted along another direction so that the intersection is this Jordan arc or a hair. So with the post-critical set, one important feature is the base Cantor set, a Cantor set formed by the closure of the union of all the point components. It has the property that for each hair, exactly one of its endpoints lies in the base Cantor set. I can give a simpler model for a hairy Cantor set called the straight hairy Cantor set, which consists of a Cantor set in the plane and a height function determining the height of a vertical line segment attached to each point, which can also be a single point if the height is 0. And this height function h satisfies the following properties. The set of all points with strictly positive height is dense in C. Also, every endpoint of the Cantor set has 0 height. It also equals the lim sup of the heights of the at points approaching it. And further, and for any other point x in C, the height at x equals the lim sup of the heights of t as t approaches x both from the left and from the right. Each hairy Cantor set is ambiently homeomorphic to the straight hairy Cantor set. Here is an example from a paper by Chiragi and Pedramfar of a construction of this height function as a uniform limit. We will for now we'll focus on only the hairy Cantor set case for the post-critical set. In general, and we will want to compute its house of dimension as well as the house of dimension of certain special subsets. In general, when computing house of dimensions, it is easier to compute an upper bound from the definition of house of dimension, while lower bounds are more difficult. However, there is a criterion by McMullen which can help. So it is for the house of dimension of an intersection of nested sequences of measurable subsets of the plane, this Kn, which satisfy certain nesting conditions. For example, every element of Kn contains at least one element of Kn plus 1, and every element of Kn plus 1 is contained in exactly one element of Kn for all n. The elements of Kn must have positive and finite area, and also two distinct elements of Kn can only intersect at a set of area 0. For example, they can here intersect at the boundary or at a single point. Then we have these diameter bounds dn for every element of Kn, which go to 0 as n goes to infinity, and these density bounds delta n plus 1 for the density of Kn plus 1, identified with the union of its elements in each element of Kn, where the density is the ratio of the areas. Then by a lemma of McMullen, we have this lower bound for the house of dimension. The upshot of this is that if we want the house of dimension of the intersection to be high, or if we want it to be equal to 2, then the diameters, dn, have to go to 0 faster than the product of these density bounds, which gives a bound for the density of k n plus 1 in a component of k0. We will construct such a nest for a subset of a hairy Cantor set, of the hairy Cantor set post-critical set, using the near parabolic renormalization of Ino and Shishikura. So we perturb a simple parabolic fixed point. So here we have this, for a parabolic fixed point, we have this incoming crescent-shaped region and this outgoing region. In the incoming region, the orbits of every point converges to 0 along an attracting direction. But if we make a perturbation, then the parabolic fixed point bifurcates into two near parabolic fixed points. We will normalize so that one of them is 0, and we call the other sigma f. And a gate opens between them, so the orbits that would have been attracted to the parabolic fixed points now pass through, and near each of the fixed points, we can find sectors landing at them, to which, under sufficiently high iterate, f returns. Then this return map, viewed in an appropriate change of coordinates, which I shall soon explain, will be the top near parabolic renormalization if the sector lands at 0, or the bottom near parabolic renormalization if the sector lands at sigma f. And also, the maps we'll be working with will have a unique critical point, and at least in the domain that we are considering for renormalization, and a unique critical value, which we will set to always be the same. And we will also define, in a similar way, the post-critical set as a closure of the orbit of the critical value. So, to be more precise, we have this simply connected region with piecewise analytic boundary. The boundary contains both 0 and sigma f, and also the critical point, which we call the perturbed petal. And on this perturbed petal, there is a univalent holomorphic map, phi, called the perturbed Fatou coordinate, which semi-conjugates f to translation by 1. We will, here, working with for a top renormalization, we'll take this half-infinite strip, send it to in the Fatou coordinate plane. Also, the perturbed Fatou coordinate sends the perturbed petal to this bi-infinite vertical strip. So we'll take this half-infinite strip, take its pre-image in the Fatou coordinate, which is a sector landing at 0, and we will take its pre-images under f until we return back to the petal. And then we'll go along a specific branch of the inverse so that the sectors always remain attached to 0. Then we will bring this sector back into the Fatou coordinate plane by the Fatou coordinate. Then we'll have this Horn map, EF, which commutes with translation by 1. So we can then conjugate with this exponential, which sends the top end to 0 and has period 1, to obtain a map defined on a neighborhood of 0, which is our top renormalization. In the bottom case, things are mostly similar, except we'll be taking this half-infinite strip going to the bottom end, and we'll have sectors landing at sigma f. But this exponential will still send the bottom end to 0. And we also normalize so that this change of coordinates sends the critical value to itself and sends it to 1 in the Fatou coordinate plane. And then we'll obtain, for our top and bottom renormalizations, they will have fixed points at 0 with multipliers. Yes, the multipliers at 0 and sigma f are denoted by e to the 2 pi I alpha f and e to the 2 pi I beta f. And then the top and bottom renormalizations will have a fixed point at 0 with multipliers depending on alpha f or beta f, as seen here. And if one of these maps is appropriately near parabolic, then we might be able to repeat one of the top or bottom renormalizations. And if we can repeat the renormalization infinitely many times, we say a map is infinitely near parabolic renormalizable. So, and we'll denote the type of each successive renormalization by kappa n, and each function by fn. Now, according to Chiragi and Shishikura, in the case for PC tau, the combinatorial type has infinitely many bottom renormalizations, but there can be, in between them, we can have top renormalizations as well. However, if the combinatorial type consists of unit fractions, that is, these continued fractions have length 1, then all the renormalizations will be a bottom type. We will focus on this case in some examples because we have some nicer properties then. So we can use the near parabolic renormalization to construct nests of open neighborhoods which shrink towards the post-critical set. We take these renormalization sectors, depending on the type, on level n plus k, then we lower them by the changes of coordinates, the compositions of the inverse to this exponential map and the inverse of the Fatou coordinate to level n. And then for this lower sector, we iterate f an appropriate number of times until it closes around itself. And we call this neighborhood omega nk. We have a nested sequence of these neighborhoods on each level in the dynamical plane of f. And their intersection is the post-critical set. I will give a more concrete example. So let's say we have f0 top renormalizable and f1 also top renormalizable. So in the union of the iterates of the sector of level 0 will just be this open connected and simply connected set, which contains 0, but not sigma 0. And the same on the next level. However, when we lower this sector and iterate it, we will still have a connected and simply connected neighborhood, but it will have these oscillations here, which depend on the distance from the points in this boundary to 0. However, if f1 is instead bottom renormalizable, then the changes of coordinates won't send. Then on this level, we have a neighborhood around sigma 1, which does not contain 0. And also, the changes of coordinates send 0 to 0 here, but they send sigma 1 to a periodic point of f0, which is denoted by sigma 0, 1. And when we iterate this lowered sector, we obtain a disconnected neighborhood. So in general, bottom renormalizations cause these neighborhoods to become disconnected. So we have infinitely many bottom renormalizations. We see that with the neighborhoods, we have a situation like here and here, where we have uncountably many connected components in the intersection. So we'll be interested in the dimension of the post-critical set, but also of its closed invariant subsets. We have one special hair called the critical value hair, which has at one of its endpoints the critical value, which lies outside of the base Cantor set, and the other lies in the base Cantor set. We can obtain all the closed invariant subsets of the post-critical set by cutting off this hair at a certain length away from the critical value, and then taking the point where we cut off, iterating it, and taking the union of its taking the closure of its orbit. Now, if we cut off at the critical value, or we don't cut off at all, then this will give us the entire post-critical set. But if we cut off all the way to the point in the base Cantor set, then we will obtain the base Cantor set. Also, if we parameterize the critical value here with the unit interval 0, 1, setting 0 to be the point in the base Cantor set and 1 the critical value, then we can have this parameterization IF for the set of closed invariant subsets, which is a homeomorphism if we equip it with the Hausdorff metric and monotonic with respect to inclusion. Now, one of my main results is that if the post-critical set is a hairy Cantor set, then for all t strictly greater than 0, the Hausdorff dimension of the closed invariant subset is 2. That is, the Hausdorff dimension is 2 for all closed invariant subsets other than the base Cantor set. Now, in order to prove this, I will adapt arguments used by Cheraghi, Dezzotti, and Young in the irrationally different case, that is when all the renormalizations are of top type. So we will extend the domain of definition of the inverse Fatou coordinate, either at the top end if we have a top renormalization, or at the bottom end if we have a bottom renormalization. We will define a change of coordinate between Fatou coordinate planes. It will be easier for us to work in the Fatou coordinate planes because there we have better estimates for the behavior of the changes of coordinate. And we will also, because the Fatou coordinate semi-conjugates f to translation by 1, we'll also be interested in translations of these changes of coordinates. Now, these chi-n are in a certain sense uniformly hyperbolically contracting, and they form homeomorphisms between the critical value hairs denoted by little gamma in the Fatou coordinate planes. And for every point, we'll denote its backwards orbit with orbit under the Fatou under the changes of coordinate, and the itinerary, which defines these translation numbers. Here to give a concrete example where Fn is top renormalizable, the change of coordinates will be defined on this domain, which is infinite towards the top end and corresponds to the one full turn of f around 0. Then above a height d over mod alpha n, the map will be nearly affine with linear part alpha n and a constant term corresponding to the periodic point obtained for normalization in the two-coordinate plane. And below, it will behave like a logarithm. So we have these oscillations, which were also seen here for these neighborhoods. And then when we take the translations one by one, they will also say tile the upper end of the two-coordinate plane. However, in the bottom case, again, above minus d over mod beta n, the map behaves like a logarithm, but below this height, it behaves like an exponential which winds around the periodic points emerging from the renormalization. And these translation images will remain disjoint rather than connecting as in the top case. So we can obtain a sequence of heights which are determined by the heights of the orbit of the point where we cut off to obtain a closed invariant subset, such that a point in the post-critical set on the 0 level lies in this closed invariant set if and only if its height is above this sequence on every level when we look at its orbit. A key part of our construction will be the critical value hairs, which will serve as a skeleton for an almost rectangular partition. We can show that these hairs are nearly vertical, and their heights yn, denoted by yn, go to infinity as n goes to infinity, to counteract the hyperbolic contraction from before. Now, depending on some epsilon greater than 0, we will construct an almost rectangular partition into these nice half boxes and almost rectangles. So the almost rectangles go between a hair and its translation by 1, and they only exist in the top case above the oscillations. We'll then take the inverse psi n of changes of coordinates, take the image of one of these nice half boxes and almost rectangles, and then pack it on the level above with nice half boxes and almost rectangles up to a uniform density, uniform positive density. Then we will lower these partition elements to the 0 level to obtain the nest we need for McMullen's criterion. We will be interested in the densities. Now, the densities will be preserved up to a uniform multiplicative constant because of Kobe's distortion theorem. And the diameters will depend on a product of contraction factors, which depend on the derivatives of the changes of coordinates. So to simplify, there are basically 3 cases. One case where these densities are bad, so we can only say that they are some uniform positive density, they are bounded by some uniform positive density, but we can't say that it's close to 1. However, the contraction factors will be good. They will tend to 0 as n goes to infinity. There is another case where the contraction factors will be bad, so we can only have some uniform bound less than 1 for them. But the densities will be good, so we can pack these elements of the partition up to some density 1 minus epsilon over 5, where epsilon can make epsilon very small. And there is a third case where we have both a bad density and a bad contraction factor. However, if this case repeats enough times consecutively, then we will be back in this case with a good density. So then if we perform the calculations, we'll get a lower bound of 2 minus m1 epsilon for the house of dimension. And then we can let epsilon go to 0 to obtain house of dimension 2. Now, in the case where all of the renormalizations are of bottom type, or in satellite renormalization terms, the combinatorial type consists of unit fractions, we observe something even more remarkable, a Karpinska type dimension paradox. The same paradox was observed by Cheragi, Dezzotti, and Young for an irrationally different case, but only for certain irrational multipliers. So this means that, the dimension paradox means that for the hairy Cantor set, in our case, the Hausdorff dimension of the set of hairs without the endpoints of the union of the hairs without the endpoints is 1, but the dimension of the union of the endpoints not lying in the base Cantor set is 2, which is surprising because we would expect intuitively the hairs to be larger than their endpoints and thus have larger dimension, but this is not the case. So one basic idea is that we use a uniform grid to cover the hairs without the endpoints, and we can show that the orbit of any point in this union of hairs will eventually lie below these kappa parabola curves, which we can then use to, if we take the image of one of these covering boxes under the inverse for 2 coordinate on the next level, we can use it to thin out the coverings by only taking boxes on the grid which intersect the area below the kappa parabola. This is just a very vague sketch of the proof. We will also be interested in the dimension of the base Cantor set, which, I want to remind you, is the closure of the union of all the single point components of the hairy Cantor set. And here it is also the set of limits of the periodic points which emerge from the renormalizations. And we can show that this base Cantor set lies between the heights yn of the critical value hairs and the heights of the periodic points emerging from the normalization, denoted by yn1, up to a uniform constant. And my main result here is that, again, in the case where all normalizations are of bottom type, or the combinatorial type consists of unit fractions, and the post-critical set is a hairy Cantor set, so this only applies to the hairy Cantor set case, the base Cantor set has Hausdorff dimension bounded above by 1. So just to give a brief sketch, we first prove this result in the case where there is a subsequence for which the distance between these two heights, where the base Cantor set lies, is uniformly bounded. Then we can use for our coverings just a collection of uniform boxes. Then using these estimates on the changes of coordinates, we can show that we have upper bound of 1. And then in the general case, where this distance can go to infinity, we take uniform boxes which cover the base Cantor set here. So we have a balance between two behaviors. Closer to these edges, the contraction factor, which depends on the derivative of the changes of coordinates, will not be very good. So it can be large in comparison to the sizes of these boxes. However, here, the heights of the boxes when sent to the previous levels will follow the periodic points, which will converge to the endpoint of the hair. And thus always taking the boxes near the edges, we can send them a uniform height above the critical value hairs. Then we can again use the same trick as we did in the previous case, when the heights are bounded. And in the middle, the heights of these boxes, when sent to the level below, can go up all the way to the height of the periodic point. However, the contraction factor there will be very large, which will balance it out. Or it will be very small, which will balance it out. So just to finish, we can obtain some examples where the base Cantor set has a particular dimension for particular combinatorics of the quadratic-like of the near parabolic renormalization. So we have attained a Hausdorff dimension of 0, of 1, and a Hausdorff dimension in this interval strictly between 0 and 1. But we don't know if there is, if we can attain any dimension between 0 and 1, or if we can make these interval bounds here more sharp. Okay, thank you for your attention, and here are some of the references. Yes.
I have two questions. So one is, I think if you like this, you can also prove that the Lebesgue measure of the critical strength is 0.
And that was already proven by Cheragi and Vedramfar.
Oh, really? Oh, okay.
But I think it's unpublished work.
Another question is, do we have like a arithmetic criteria for when the hairs come out? Like kind of like reading-like function that determines whether the hairs exist or not?
Yes. It is more like the Herman criterion for, yes, it's like Herman-Jochens-like condition, which depends on the combinatorial type. So basically, in my setting, it would mean do the periodic points under, when the changes of coordinates are applied, do they converge to the critical value, which is 1 in the two-coordinate plane, or not? If they do, then we have a Cantor set.
Other questions? So I'm just trying to make sure I understand, because you were saying that for some of your examples, you're able to show that the hairs have dimension 1.
Yes.
But the ends of the hairs have dimension 2.
Yes.
But you also showed when you take these dynamical invariant subsets of the post-critical set, but are those not contained in the hairs?
Not exactly. There are certain hairs which are wholly contained in one of these invariant subsets.
Any other questions? Okay.